Hey everyone, welcome back to the deep dive. We're all about getting to the heart of complex topics here, and today we're diving into something that's, well, pretty fundamental to how reliable the software we all use every day actually is.
Yeah, that's right. We're talking code coverage. And understanding this gives you a real insight into how software is tested, put through its paces to hopefully make sure it works as it should.
Basically, it's a way of measuring how much of a program's code has actually been tested. We've got a great tutorial here that lays out the different methods for tracking this, and we're going to unpack it all, explain it all, so you can really get a handle on it.
We're going to extract those key insights for you. By the end of this deep dive, you'll understand what code coverage is all about, why it's so important, and the various techniques, and even some of the tools that get used.
Yeah,
It's your express route to understanding this crucial aspect of software development.
absolutely. So let's jump right in, shall we? The tutorial starts off by introducing the concept of statement coverage.
And the core idea here is to make sure that every single line of executable code in a program actually gets run at least once during testing.
Hmm.
That's statement coverage.
Okay, so it's like looking under the hood, actually peering at the software's internal structure, the code itself. And with statement coverage, you're making sure that each instruction, each line of that code is actually executed, like checking off steps in a recipe as you go.
Precisely. And to measure this, there's a pretty straightforward formula. You take the number of statements that were actually run during your tests, you divide that by the total number of statements in the entire code, and then multiply by 100 to get a percentage. That gives you a nice quantifiable way to see, how much of your code is actually being exercised by the
I
tests.
like that. I like having the numbers, makes it concrete. The tutorial gives a couple of scenarios using a bit of code. It's a little function, pretty simple, that takes two numbers, A and B, adds them together to get a result, and then it tells you if that result is positive or negative. So in the first scenario, they use A3 and B9 as the input.
Okay, so if you run that code with those inputs, the lines that define the function itself, they get executed. And the calculation of the result, which in this case is 12, that happens. Then the condition, checking if the result is greater than 0, that gets evaluated. And it's true, right? So the line that prints positive to the screen, that gets run. The other option, printing negative, that's skipped because the result is positive. And then finally, the end of the function, that's reached. So in total, that's 5 lines of code that were executed.
Right. And the tutorial points out that there are 7 lines of code total in that little function. So 5 out of 7 executed, you do a little math, and that means that specific test achieved roughly 71% statement coverage.
Exactly. Now, they've got a second scenario where they use different inputs. They use A equals 3 and B equal -9. You can walk through it again. The function definition, that's executed. The result, now it's -12, that's calculated. But this time when you check if the result's greater than 0, well, it's not. It's false.
So it takes a different path.
Exactly. It skips the positive line and instead executes the line that prints negative and then again reaches the end of the function. In this case, we've executed 6 out of the 7 lines.
Which gives us, let me see, about 85% statement coverage. Okay, I'm starting to get the picture here. By doing both of these tests with the positive and negative results, we've essentially made sure that every single line of that little piece of code has been run at least once. And that, as the tutorial highlights, gives us 100% statement coverage.
That's right. Across both of those tests, all 7 lines have been touched. But, and this is really important to understand, it's crucial to also know what statement coverage doesn't tell us. Even if you have 100% statement coverage, you might have parts of your code that are never actually used, what we call dead code, or different paths through your code that your tests haven't actually explored yet. And critically, it doesn't tell us if we're missing some code in the first place.
Right, right. So just because every line has been run doesn't mean that we've tested all the different decisions the code could make. And that kind of naturally leads us to the next type of coverage the tutorial talks about, decision coverage, sometimes called branch coverage.
Right, and this is where things get interesting. Decision coverage, it's not just about the individual lines, it's about the outcomes of those true or false conditions in your code,
Mm,
making sure that every possible result of each of those decision points is tested.
got it. It's not just about running the code. It's about making sure we've gone down all the different paths, all the different routes the code could take based on those if this, then that scenarios. It's like exploring a maze and making sure we've taken every possible turn.
Absolutely. And how we measure it, it's about looking at how many of those decision outcomes we've tested compared to the total number of possible outcomes, again, expressed as a percentage.
Okay, numbers again. I like it. The tutorial uses another little bit of code to demonstrate this. It's a function that takes a number, let's call it a. If a is greater than 5, then a gets set to 3, and then the value of a is printed out. So in one scenario, they use an input of a being 2.
Right. So in that case, the condition a greater than 5, well, 2 is not greater than 5, so that condition is false.
Hmm.
What happens then? The part inside the if block where a would have been set to 3, that gets skipped entirely. And the code goes straight to printing the current value of a, which is still 2. So we've tested the no outcome, the false outcome of that decision, that a greater than 5.
Makes sense. And how does that fit into the decision coverage percentage?
Well, for that decision, there are two possibilities, right? True or false. We've tested one out of the two. So that gives us 50% decision coverage for this particular test.
Okay, so one scenario down, 50% coverage. What about if a was 6?
Now that changes things. If a is 6, then the condition e greater than 5 is true. So the code inside that if block gets executed, and a is set to 3. And then the value of a, which is now 3, is printed out. So in this case, we've tested the yes outcome, the true outcome of the decision.
Again, one out of the two possible outcomes tested, so 50% decision coverage for this test too.
Exactly. And this is where it gets interesting. The tutorial shows a handy table, and it highlights that if you ran both of those tests, one with a 2 and one with a 6, you'd actually achieve 100% decision coverage because you've tested both the true and the false path, both outcomes of that if condition.
Ah, okay, I see. So it's about making sure you've covered all your bases, all the yeses and nos. Now, the tutorial also talks about branch coverage, and I'm a little fuzzy on this. Is that essentially the same thing, or is there a subtle difference there?
It's a great question, and it can be a little tricky. Branch coverage, as the tutorial explains it, is about making sure every outcome from a piece of code, whether it's a single statement or even a loop, is executed. It's about ensuring you've gone down all the possible paths or branches, hence the name, that your code can take. And yes, for those if statements with a true or false outcome, you need to test both to achieve full branch coverage.
Okay, so it sounds very similar. Even the formula they give is the same. The number of executed branches divided by the total number of branches expressed as a percentage.
You're right, they are closely related. In many practical situations, achieving 100% decision coverage will also mean you've got 100% branch coverage, and vice versa. But there can be subtle differences, particularly when you start looking at more complex code structures. Let's go back to that little if a greater than 5 example. The tutorial even has a diagram, and it shows two branches stemming from that condition. One branch, if a greater than 5 is true, and another implicit branch, what happens if it's false. Sometimes, thinking about branch coverage, you might even consider the entry point of the function as a branch itself.
Okay, so if we look at the branch coverage results in the tutorial, for that test with a 2, where the condition was false, it says 33% branch coverage. And for a 6, where it was true, it's 67%. It sounds like maybe they were thinking about 3 potential branches there, entering the function, the true path of the if, and the false path, the rest of the code.
You've hit on a key point. The tutorial itself even mentions that those percentages in the table could be seen as focusing just on the true or false outcome of the if statement itself, treating it as 2 branches. In that case, each scenario would give you 50% coverage. The broader view, the more comprehensive way to look at branch coverage often does consider all those potential paths, all the segments of code. The key takeaway is that to get that full branch coverage, just like with decision coverage in this simple example, you need tests that cause both the true and false branches of that if statement to be executed across your entire set of tests. And different tools might calculate it slightly differently, but the core idea is the same.
Okay, I think I'm starting to wrap my head around that. So even if the exact numbers might vary, depending on how you're measuring it, the main idea is to make sure your tests exercise all the different paths the code could take. Now, zooming out a bit, we've been talking a lot about this code coverage stuff, but why should someone who uses software, why should you care about all this? Well, the tutorial actually lists a bunch of benefits, and they're pretty compelling.
Yeah, and these are reasons why, developers and testers, they pay close attention to this stuff. For one thing, it gives them a way to measure how effective their testing actually is. It's not just about, writing a bunch of tests. It's about seeing concretely how much of the actual code is being put through its paces by those tests. It helps them identify gaps, areas where they might need to focus more testing.
Makes sense. It's like having data to back up your testing efforts. And the tutorial also mentions that it helps to validate all the different paths in the code, making sure that no particular route leads to some unexpected problem.
Absolutely. By finding the parts of the code that aren't being tested, It almost guides you to create better, more comprehensive tests. It's about making sure you're not just testing the happy path, the most common scenarios, but also those edge cases, those less frequently used parts of the software that might hide those tricky bugs.
And I guess importantly, it can help find those hidden parts of the program that might be more likely to have errors simply because they haven't been properly tested. It's like shining a light on those dark corners. But like any metric, there are limitations, right? Relying only on a high code coverage number can be a bit misleading.
Exactly. That's a crucial point. The tutorial is very clear about this. Even if you get that magical 100% code coverage, whether it's statement or branch coverage, it doesn't automatically mean the software is bug-free. It's not a guarantee. For you as a user, that means that even well-tested software can still have issues. Code coverage doesn't tell you, for example, if all the possible ways a feature might be used have been tested, with all the different kinds of data it might encounter in the real world.
Right, so just because a line of code has been run doesn't mean it'll work correctly with every possible input it might get. The tutorial also points out that code coverage doesn't guarantee the absence of logic errors, especially in those more complex, intricate parts of the software.
Exactly. If the underlying logic of a function is flawed, if it doesn't do what it's actually supposed to do, even if all the lines of code within that function are tested, those fundamental problems might still be there lurking. And this is a big one. If a feature or a piece of functionality is simply missing, it's supposed to be there, but it's not in the code at all, well, having high code coverage for the existing code isn't going to help you there. It won't flag that absence.
So code coverage, it's a useful indicator, but it's not a silver bullet, right? It tells you what has been tested, but it doesn't guarantee that everything has been tested or that what was tested is actually correct. Now, the tutorial goes on to mention a few other types of code coverage beyond statement, decision, and branch. It mentions toggle coverage and FSM coverage, but it doesn't go into a lot of detail.
Yeah, it keeps it pretty high level, just acknowledges they exist.
Mm-hmm.
I think for the sake of our discussion, we'll do the same, just acknowledge that there are more specialized ways of looking at this. But the tutorial does say that finite state machine coverage, FSM coverage, tends to be the most complex type, as it looks at how many specific states the software can be in, how it transitions between those states, over time.
Sounds like it gets pretty intricate. They also make a really interesting distinction between code coverage and functional coverage, which I think is particularly relevant for understanding the bigger picture of software quality.
Yeah, and this is really important to understand. Code coverage, as we've been talking about, is about how well the tests exercise the actual code itself. It's often something developers focus on a lot as they're writing and doing their unit testing of their code. But functional coverage, that's about looking at how well the actual features and capabilities of the software, as defined by the design and the requirements, how well those have been tested. That's often a big focus for testers who are evaluating the software from the user's perspective.
Ah, okay. So it's like two different lenses, two different perspectives. One's more about the nuts and bolts, the implementation, and the other's more about whether it actually does what it's supposed to do from the user's point of view.
Exactly. Code coverage is asking, did we run this piece of code? And functional coverage is asking, did we thoroughly test this feature that you as a user would interact with?
I like that. That makes it very clear. Now, last but not least, the tutorial gives a list of some of the tools that developers and testers actually use to measure and analyze code coverage. There's quite a few out there, isn't there?
Oh yeah, there's a whole bunch.
Yeah.
The tutorial mentions Cobertura, which is pretty widely used, especially for Java projects. It measures both lawn and branch coverage. Clover is another popular one for Java, and it has this neat feature where it can actually help to speed up testing by only running the tests that are relevant to the code changes you've made.
Ah, so that means faster development and potentially quicker updates to the software we all use.
Exactly. Then there's Dev Partner, which helps analyze Java code for things like quality and complexity. And Emma, another Java tool, but it supports different levels of coverage, from individual lines to whole methods or even entire classes.
It's like having different magnifying glasses, right? Different levels of detail.
Exactly. They also mention Callistic, which is interesting. They describe it as a tool that can analyze your code from different perspectives, giving you a more holistic view. And then you have CoView and CoAnt, which offer a whole suite of features. They can do metrics. They can help you create code that's easier to test. They can track your path and branch coverage. And if you're working with C++ or C, there's Bullseye coverage. And finally, there's Sonar, which is kind of a platform that helps you manage the overall quality of your code and code coverage is a big part of that.
Wow, that's a lot of tools. It's good to know that there are tools out there that can help automate this process. I mean, trying to keep track manually of which parts of your code have been tested, that would be a nightmare for any real-world software.
Oh, yeah, absolutely. And these tools, they often integrate right into the development process. They're giving developers and testers that real-time feedback on how effective their testing is, and that just helps to build better software in the end.
Absolutely. Okay, let's bring it all together. Let's summarize the key takeaways from our deep dive into code coverage.
All right, so first and foremost, code coverage. It's a measure of how much of the code has actually been executed during testing. It's a fundamental metric for understanding how thoroughly a piece of software has been tested. The tutorial highlighted 5 main types: statement coverage, decision coverage, which is often closely tied to branch coverage again, noting the subtle differences in interpretation there, toggle coverage, and FSM coverage. Each one's looking at a slightly different aspect of how the code runs.
Right. So, with statement coverage, it's about making sure every line has been run. Decision and branch coverage are about making sure we've explored all the different outcomes of the decisions in the code, all the yeses and nos, and all the different paths that the code can take based on those decisions. And the other types, those get into more specialized areas, the more complex behaviors of the code.
Exactly. And it's important to remember that while a higher code coverage number usually means that the software has been tested more thoroughly, it doesn't automatically mean that the software is free of bugs or that it meets all the requirements. It's a valuable indicator, but it's only one piece of the puzzle. Choosing which types of coverage to focus on really depends on the specific needs of the project, the cost of testing and the risks involved. And as we saw, there are a lot of great tools out there to help you measure and analyze your code coverage.
So by understanding code coverage, you get a much better appreciation for the work that goes into making reliable software, the steps taken to make those apps and programs we all use as robust and dependable as possible.
Absolutely. And it's interesting to think about how this idea of measuring coverage can be applied beyond software. Think about any system or process you interact with daily, like how your car engine works, or the process of getting a package delivered to your door. These all have some kind of underlying logic, a set of steps or decisions. And you can think about how that logic might be tested. What kind of coverage would be most critical to make sure it works reliably every time?
That's a fascinating way to think about it. It's like a new lens to view the world through, to see those hidden complexities. Well, thanks for joining us for this deep dive into the world of code coverage. Until next time, keep those brains buzzing, keep thinking critically.
And we'll see you on the next deep dive.
See you then.